So what we have seen is the following. We are studying representations of C of x, and also along with that, the corresponding representations of C of x, which are extended to L infinity. So that's what we want to study more on that. So if so x is, of course, as before, x is something x contained in C or R, whatever. C is compact. Then mu is a measure, mu finite measure on x. Then we have this representation pi mu from C of x to B of L2. Then we have extended this. Then there exists we proved that there exists a unique extension pi mu tilde from L infinity of x mu to B of. It's the same multiplication representation. It's just multiplication representation. It's the same multiplication. So we want to prove a lemma. We also proved that that representation satisfies something converges mu almost everywhere. I mean, if a sequence of functions which are uniformly bounded and it converges mu almost everywhere, then it converges strongly. So we want to prove something, an equivalent thing. So as before, we have all these things. Suppose we have a Fn contained in L infinity, okay, such that supremum of Fn. So shall we assume that before, or less than infinity? Then so I have already defined some convergence in measure. So we have any convergence for functions. I mean, when we have functions on measure space, so we define something called convergence with respect to a measure. So the condition is then Fn converges to F is also an infinity in mu, okay, is equivalent to saying pi tilde Fn mu converges to pi tilde of F strongly. Strongly means it's point-wise convergence in the corresponding Hilbert space. That here the Hilbert space is L2 mu. Proof. We had proved one way that if it converges mu almost everywhere, uniformly bounded, which is basically Lebesgue-dominated convergence theorem. And here also we are going to do that. So suppose F1 converges to F. Okay. That means what? That is this mu of this set x in x such that Fn minus F Fn x minus F of x, this set greater than or equal to epsilon or any number goes to 0 for all epsilon. Okay, that's the meaning of, that's the definition of convergence in measure. So suppose this goes to 0, okay, then we want to prove strong convergence. So let G is in L2. We want to prove pi mu tilde of Fn minus F. We want to say that Fn minus F acting on G goes to 0 in L2. That is integral over x mod Fn minus F square G mod G square d mu. If you want this to go to 0. And this is equal to integral over where Fn minus F is greater than or equal to epsilon plus integral over Fn minus F less than or equal to epsilon. Okay? But since this is uniformly bounded, this Fn minus, so here we will have this, whatever the integrand we have. Okay? And integrand is uniformly bounded. Okay? So You can, I mean, so assume that Fn minus F, all these G, they are all smaller than constant, smaller than some constant. Let Fn minus F, this norm infinity, and G norm infinity, all those things are small, I mean, times G norm infinity if you want. Times G norm is less than or equal to some K. So then this is less than or equal to some K times mu of Fn minus F greater than or equal to epsilon. And the next thing is that is less than epsilon times, I mean, you can take Fn minus F is less than epsilon. So that you can take it out, epsilon square. See, there are two epsilons coming here. So epsilon square times norm of norm G2, right? Norm G2. Oh, here it is G is in L2. No? Okay, you can just there Fn minus F is smaller than we can take to be smaller. Then we have G over that. G is in L2, but something is L2 for a finite measure. For it to be integrable, it need not be bounded. So this is not really true. See, this is not true actually. I have said that this is less than this, which is not true. I mean, G is in L2. It need not be in L infinity. So maybe I'll cancel all those things. I want to say that this goes to 0. Anyway, let me just use a completely different argument. I think one can do this epsilon delta argument, but there are two epsilons. I mean, there is, see, you have an epsilon where this mu of Fn minus F greater than or equal to epsilon, this goes to 0. So you have to find a small epsilon to make the other integrand less than something very small. Then you have to make this, you have to, for that epsilon, you have to find some eta or something so that this becomes very small. I don't know, it's becoming complicated. So I will not use this argument. I will use a different argument. Okay? The whole file has gone somewhere. So we have proved that almost everywhere convergence for uniformly bounded sequence of L infinity functions, the convergence, there is a strong convergence. We have proved that. So I will just use that, what we have already proved. Okay. So we have that Fn converges to F in mu. Okay. Then for all subsequence, Fn k, for all subsequence contained in Fn k, there exists a further subsequence. If Fn converges to F in mu, in measure, so you take any subsequence that will also converge in measure. And for that subsequence, there is a further subsequence. There exists a further subsequence such that, which I denote some, subsequence which converges to, let me not write what is said, which converges to F, which converges to F almost everywhere, mu almost everywhere, right? So you take a subsequence of this Fn, then there is a further subsequence which converges to this almost everywhere. This implies pi of Fn minus F, pi tilde of Fn minus F, G goes to 0 in L2. Okay, not Fn minus this subsequence, whatever that subsequence. Phi n phi tilde of this subsequence. Subsequence of the subsequence that I am just calling it as subsequence of G goes to pi tilde mu of subsequence, no, not subsequence, this F. G. Okay. So this just means that this has this property. If you consider this pi tilde mu of Fn, this pi tilde mu of Fn, this sequence, pi tilde mu of G, this sequence, okay, this is a sequence in that this is something contained in L2 mu. Okay. This sequence has a this sequence has the following property. This sequence, for all subsequence of this sequence, there exists a further subsequence which converges to pi mu of F, L2, pi mu of Fg. Okay. I mean, what I mean is this for all subsequence of this pi mu tilde Fng, there exists a further subsequence converging to pi mu tilde of Fg. This is an element in the Hilbert space. Pi tilde mu Fg is an element in the Hilbert space. This pi tilde mu Fng is an element in the Hilbert space. Hilbert space is a metric space. Okay, and this sequence, particular sequence, satisfies the following property. For all subsequence, there exists a further subsequence which converges to this number, this element, Hilbert space element. That will imply that the sequence itself converges to this. This is a general fact in the metric space. If you have any sequence which has the following property, this is an exercise. Okay, in a metric space. Okay, this is an assignment. Okay, this is an assignment. It's a very easy assignment. If you, in any metric space X and you have a sequence Xn contained in X satisfying for all subsequence of Xn, there exists further subsequence converging to one single element X in X. Then the original sequence Xn converges to X. Okay, this is an assignment. This is easy to do. Okay. So once
so the limit is common for all subsequence, right?
Exactly. That should be the case. Yeah, the limit should be same, right? Okay. Once you have the same limit, so you have a sequence which has the following property: for all subsequence, there exists a further subsequence. All those further subsequence converging to same limit X. Then the original sequence also converges. So that is what I am using here. Okay, I am unnecessarily confused, but the point is, see, the point is convergence in measure does not imply convergence almost everywhere, because see, there this will not work, but when we use it here, it works. I mean, I don't know whether I'm unnecessarily complicating, but the point is, in the Sundar's book, it says that it follows from dominated convergence theorem, and I don't see why. I went through an argument, but it looks it's getting that's messy. But this is direct. Even though the way I said is complicated, though there is nothing complicated. I'm saying if mu Fn converges to F in mu, then that means convergence in measure implies a subsequence converging almost everywhere. Mu. But if you take any subsequence of this, which also converges in measure, there is a further subsequence which converges almost everywhere. That will imply a convergence, strong convergence for the corresponding sequence in the Hilbert space. So then this Hilbert space thing satisfies the strong convergence property, so you get the strong convergence. Okay? But then that you cannot apply to the mu convergence, I mean almost everywhere convergence, because each time when you say almost everywhere convergence, the almost everywhere convergence is you remove a set of measure 0, outside that it converges. But for each subsequence you have a set of measure 0, but when you want to take I mean, that doesn't really imply that it will not be possible to get one single set for the original sequence. One single set of measure 0 for original sequence. You have to take union or something, but it will not be a countable union, so it will not work. Okay, so that will not work there. But here it works. Okay, so I think the proof is okay. So these things implies that this Hilbert, and I'm using only Hilbert space convergence for this particular element G. So this works for that. Okay, you go through it. If you see a problem, you tell me, or if you have a doubt now, you tell me. Okay. So convergence in measure implies the corresponding convergence in strong convergence for the corresponding representation of the corresponding functions. Okay, so this way is proved. So let us prove the other way. Other way is easy. So suppose pi mu tilde of Fn converges to pi mu tilde F. Okay, in in strong convergence. Strongly. So strong convergence means you apply on any Hilbert space element, it converges. In particular, you have this G0 equal to 1, which is in L2. Okay. So you apply for this. That implies that integral mod Fn minus F d mu goes to 0. I mean, square goes to 0. But then mu of Fn minus F greater than or equal to epsilon is greater than or equal to epsilon. So it is less than or equal to 1 by epsilon square integral mod Fn minus F square. This maybe this square. No, this is fine. Yeah, Fn minus square dv. So this is less than or equal to this. And this is certainly less than 1 by epsilon square of integral mod Fn minus F square. And this is over this set Fn minus F greater than or equal to epsilon. On this set, you integrate it on this set, then it's on the integrating on the whole set. Okay, this is less than or equal to, because it's positive, so it's integrating on the less than or equal to. Okay, so this goes to 0. So it's fine. So other way we have to. Okay. So we have proved that for the particular representation pi mu tilde, the convergence in measure of the functions is equivalent to saying convergence in strong convergence. Okay. Now we want to consider once. So we have proved that if you have any representation, we have classified the representation of C of x. If you have any representation pi of C of x, then there exists a countable collection of measures, finite measures, such that that representation is unitarily equivalent to direct sum of the corresponding pi mu n. Pi mu n is a multiplication. I mean, every measure gives a L2 mu, and on the del2 mu, C of x acts as multiplication representation. So given any representation, you have a countable family of measures, and you take the direct sum of all the L2 mu n, and then you have the direct sum of all representation pi mu n on each of them. So that gives one single representation, and that is how every representation of C of x will look like on a separable Hilbert space. Okay, so we want to extend that representation to L infinity. That's what we want to do. So we want to prove the following theorem. Okay, so let pi be. We want to extend it, and we want to write it as a general theorem. Pi from C of x to B of h or B of h. H is separable. Which if I don't assume, also it's always we assume that h is separable. Okay. 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 Then there exists a family mu n. This may be finite, but then I mean, if it's finite, then you have to consider a finite collection. Okay. I mean, I'm writing it as an n because, but then if it is finite, you have to take finitely in many of them. Okay. So or you can call some subset of natural number or something. But the proof will work for finite. Proof will certainly work for finitely in many of them. There exists mu n such that maybe we can change it. okay, mm, such that pi is unitarily equivalent to direct sum of pi. Now define mu. We define a new measure, mu equal to summation epsilon n equal to n in I. Okay, with summation epsilon n. You can just take 1 by 2n or something, but you can take any epsilon n. 1. Okay, then 1 mu of e equal to 0 is equivalent to saying mu n of e equal to 0 for all n. This is just clear. Okay, where each epsilon n is greater than 0. Then this is clear. When we have each epsilon n greater than 0, this is clear. So that is one thing. Then second thing is second thing. Yeah. If Fn contained in L2 of mu, with, then with supremum n is less than infinity, then f no sorry, it's just a single f for any f. Sorry. For f in L infinity mu. Okay. So the norm f infinity is equal to supremum of n norm, just to denote L infinity mu, supremum of f L infinity mu. Okay. This is just, or I think maybe I will. F in L infinity mu, if and only if, shall I say, is equivalent to, this implies f is in L infinity mu n for all n. Norm f L infinity mu is equal to supremum of n norm f L infinity mu. Actually, the other way is also true. This supremum has to be, I mean, f is in L infinity if and only if f is in L infinity of mu n for all n, and the supremum of all this f in infinity is finite. Okay. Okay, so now it's clear. These are all very easy things. Maybe I will prove this and then go to the next part. That's the second part of maybe I'll say, okay, I'll state the second part of the theorem. The second part of the theorem says that if you have a phi n, which is contained in, so what is it I want to define an isometric. We have a representation pi of c of x. Okay. Then we have a family of mu n measures. Using that measure, we got a single measure out of it. Okay. Now we want to define, using that single measure, we have a L infinity mu, and we want to define something using that. So now define See, the point is the following. Pi is equivalent to pi mu n. This is by some unitary, okay? Direct sum of pi mu n. Okay? Then each pi mu n, there is a pi mu n tilde for that. Now you can take the direct sum of pi mu n tilde. Okay? Now but using the same unitary, you can make pi tilde. You understand what is happening? So there exists so wherever this pi is acting on B of h, there exists a pi tilde, which is basically the direct sum of pi mu n tilde. See, it happens like the following. Pi is a representation of C of x to B of L2 mu. Okay. Then there exists, this pi is unitarily equivalent. There exists a unitary from L2 mu, sorry, not L2 mu, h. Pi is something on h. Then there exists a unitary from h to direct sum of L2 mu n. Okay. Yeah. Direct sum of L2 mu n, which you can write it as L2 mu or whatever. Okay. Pi tilde mu we want to define, or pi tilde this. Okay. Such that this u pi u star, so u star will bring it here. This is equal to direct sum of pi mu. Okay. Now you define pi tilde by u pi tilde of u star of direct sum of pi mu n tilde. When we have pi mu n, you have a pi mu n tilde. Okay. Now using the same unitary, you can define pi tilde. Okay. Is clear? Is fine? I'm sorry, is everyone following? Shall I go
Yes,
through?
sir.
Anyone wants me to go through the argument? I'm just saying that if you have any representation of C of x, okay, that looks like direct sum of pi mu n for this mu n, collection mu n. Okay, I mean it's unitarily equivalent to that. So each pi mu n admits a representation of L infinity of x, L infinity with respect to that mu n, okay, which is pi tilde mu n. So you have an L infinity of that point is that this pi tilde is a representation. I mean, so yeah, that's the point. If you so the point is if you have f is in L infinity mu, then f is in L infinity mu n also. So pi tilde pi mu n of f makes sense, right? If f is in L infinity of mu, okay, then we have, I mean, that's what we say here. Then f is in L infinity of mu n also. Okay, so pi tilde of, so if you have pi tilde of f of mu n makes sense. Okay, so I'm just saying that you can define pi tilde mu n as by, so I mean you can take the u on that side if you want. Okay, pi tilde of f u star equal to direct sum of pi mu n tilde f. Okay. This is because pi tilde mu n of, sorry, no f. This is because pi tilde mu n of f makes sense for each n. Okay, so you can make sense. So then you can take the direct sum, and using that unitary, you can bring it here. So if you want, you can put the unitaries there, okay, because you want to define it. So Yeah, you can put the unitaries here. Okay, so you can define pi delta f like this. Okay, so pi delta f is clearly defined, well defined, and this is just it's a representation is clear because they are all representation. You are just taking direct sum. You are writing it's a diagonal operator on the direct sum, so it's clear. Okay. Okay. Anyway, so we have defined. So this is for all f in. This is defined for all f in L2 mu. Okay. Sorry, L infinity mu. L infinity mu. Okay. This representation is on H only. Okay. We have a pi acting on this. Then we define a pi tilde f on that. So this pi tilde is a unique extension. Okay. This is a pi tilde is a pi from C of x to L infinity of x mu. Okay. It's an extension on that. Further, it's is a unique is a maybe I will write down everything, all the statement. So unique isometric extension of pi. Okay, from C of x to L infinity x. Satisfying. I mean, the uniqueness comes from this property. Satisfying. Fn converges to f in mu. Okay, implies is equivalent to Fn converges to f. I mean here mu fk. Fn okay mu m. Okay, for all m. Which is equivalent to saying pi tilde of here there is no n or m. Pi tilde is just an extension of pi. Using that unitary, we bring it. Okay, pi tilde of Fn converges to pi tilde of f strong. Okay, I have written so much. This is just to. So let me recall what are all the things I have done. Okay, so this is just a construction. There is not much to prove in this. The proof is very easy. One has to just understand the construction. So I started with the representation. Pi. Okay, so you have a representation pi of C of x, which is continuous functions of the metric space x. Then our earlier theorem says that using Zorn's lemma, it says that there exists a sequence of measures mu n such that this pi is equivalent to pi mu n. Now using that pi mu n, which is on the direct sum of whatever, for each pi mu n, we get an extension of pi tilde mu n for L infinity mu n. But then we defined a single measure out of all those things, which is then we consider that pi tilde mu. So then if some f is in pi tilde mu, if and only if that f is in pi tilde mu n for all n. So now if you have an f in L infinity of mu, then using that pi tilde mu n of that f and take the direct sum of that, then you get a single representation pi tilde. Then use the same unitary to bring it and get a single representation pi tilde mu. Pi tilde. Okay, and that's a representation of L infinity. Okay, and that L infinity representation satisfies the property that Fn converges to f in mu, which is of course equivalent to Fn converges to f in mu m for all m, or all those measures, which is equivalent to the strong convergence. So this is just a unique thing. The extension is unique. Uniqueness is clear. Isometry is clear. All those things we have already proved. Anyway, we go through all that. Okay, so 550. So what is the first thing? Okay, so since I am repeating it so many times, it should be clear now. Okay, now I am going to repeat the whole thing again. So we start with the representation pi from C of x to B of h. Okay, so that gives a measure, that gives a sequence of measure, which we have seen in the last class. Sequence of measure mu n, such that pi is equal to pi mu n. Now we are defining a new measure. Now we forget about all those representation and everything. Using that sequence of measure, we define a new measure mu, which is equal to summation epsilon n mu n, where you take some numbers, some real numbers, epsilon n greater than 0, such that summation epsilon n equal to 1. Okay. Now it's clear that mu of e is equal to 0 if and only mu and e is equal to 0, because each epsilon n is greater than 0. This is just clear directly. It's direct and it's clear. Now we want to prove the second thing. So this we want to prove. Okay, this we want. So this thing says that f is in L infinity. F is in L infinity if and only if f is in L infinity of mu n for all n, and the L infinity norm of f is just the supremum of L infinity norm of each with respect to each of those mu n. So let us verify that. Okay. Now f is in L infinity of mu n. Okay. So I don't know whether I mentioned orally or something. L infinity is defined as an infimum of some numbers m. Okay. But then that infimum is actually attained. I mean, the infimum of all those m, L infinity norm of this, L infinity norm of this equal to infimum of all those m, such that mu of this mod f greater than m equal to 0, right? But then that infimum is in fact attained. The reason is so if there exists a mn which decreases to f, right? There exists a sequence mn which decreases to this. Okay. But then this mod f greater than this mn, this set increases to mod f greater than or equal to whatever, greater than or equal to whatever. It doesn't matter. Norm of greater than norm of infinity, right? This set increases to that. So mu of this thing will increase to that, and mu of all these things are 0. So this implies mu of norm f greater than norm f infinity. Norm f infinity is just a number, some m, is also equal to 0. Okay. So there exists a set. There exists some set f contained in X with mu of f equals 0. Okay. And mu of f equals 0. And norm f infinity is equal to supremum of x in f complement. Supremum of x in f complement. I mean, f complement is taken in that x, not in whole of C. Okay, this is set minus x minus f. Is clear, right? I mean, we have this set norm f greater than or equal to that, that's equal to 0. So you remove that set. Okay. And the norm f infinity looks like this. It's actually, you can write it as a supremum over some set. Is this clear? If it is not clear, I mean, this is the supremum. If this is not the supremum, I mean, whatever we have verified there implies that this is the norm f infinity is less than the supremum. Okay, but if it is not that supremum, then that will contradict that infimum property of that. There you will find something less than that. That something, I mean, so that there will be exist some other m such that something will happen. Okay, so it's an exercise.
Yeah.
Okay, so norm f infinity is actually supreme. You can write it as a supreme. Okay, okay, fine. So why do I want to do that? Because I want to talk about this supremum. Okay, norm f infinity equal to this. Okay, now this is also okay. Now I want to consider this. Let Fn equal to f union of on the set where d mu n, this is the Radon encoding derivative, d mu equals 0. You take that set. Okay, I mean x such that d mu n x equal to the set where this Radon encoding derivative vanish. Okay, then mu of Fn equals 0, of course. Okay, okay. Mu n of Fn equals 0. Mu n of Fn equals 0. And intersection of Fn, if we take intersection of Fn, okay, then mu m of intersection of Fn, of course, which is less than or equal to mu m of Fn, which is equal to 0. So this implies mu m of Fn equal to 0 for all n. This is integration over. So for all n. This implies mu of intersection of Fn equals 0. Right? Okay. But F is contained in, I mean, this F is contained in intersection of Fn. So these things implies that norm F infinity, you remove the set F and take the supremum over that set. But we can remove a bigger set which measures 0. That doesn't matter. Okay. So norm F infinity equal to supremum of x in F. Oh, sorry. Supremum of x in intersection of Fn. I made a mistake. Okay, that's okay. Intersection of Fn. Intersection of Fn is not equal to F. It's a slightly bigger set than F. Okay. Intersection of Fn mod of f of x. This is okay. I mean, norm F
Like, what is the definition of Fn?
Fm.
Fn.
Fn is Jeff union wherever the Radon encoding derivative d mu n by d mu vanish. Radon encoding derivative vanish. So on that what is Radon encoding derivative? Which is just, I mean, which mu n is absolutely continuous with respect to mu. If mu n of some set equals 0, sorry, if mu
okay.
equals 0, mu n is 0. Okay. So there exists a Radon encoding derivative for that.
Okay.
So wherever that Radon encoding derivative vanish for each n, okay, I'm attaching that set to F, so that mu n of this Fn equals 0. But if you take the intersection, then mu m of Fn, that intersection is 0 for all n. So mu of that set is also 0. Okay. So that is a slightly bigger set than the original set we considered, where we took the supremum. Okay. But still that set measure is 0. So the L infinity norm does not matter if you remove a set of measure 0. So norm F infinity equal to supremum of x in intersection Fn of f of x. Okay, that's what I'm saying. Okay. Okay. Now this is same as supremum over, sorry, intersection of Fn complement. Sorry. Not intersection of Fn. Intersection of Fn complement. There are also right complement. Yeah, there are also everything. The complement is x minus. Okay, it's a complement. So which is same as supremum of x in, which is same as supremum over n. Okay. Supremum over, the complement is the union of each of the single one. So supremum of f of x, this is x is in x minus Fn. Right? Okay. Okay. Now this x minus Fn, I mean this which is equal to supremum of n. See, this x minus Fn has mu n measure 0. Okay. I just want to say that this is same as norm f with respect to L infinity mu n. Fn has mu measure 0, and that mu of, I mean, it's a supremum. Yeah, So what is the L infinity of something? It is a, I mean, it's a supremum over. It's clear. I'm just wondering how to say. See, we have this radon nicotine derivative. See, what is this Fn? It is where precisely. I mean, if you go out of this set Fn, the radon nicotine derivative is strictly greater than 0. Okay, the radon nicotine derivative of d mu n by f is strictly, so it's absolutely continuous with respect to that. So L infinity norm of anything in that set is a, see, L infinity does not depend on the measure. It only depends on the absolute continuity of the measure. If you replace a measure by a similar measure in the which has the same absolute continuity with respect to that measure, the L infinity norm remains same. Okay, so the outside this set Fn, the L infinity norm of f with respect to mu is same as L infinity norm of mu n. Okay, so you are, should I write all these things? But I think it's clear. But I'm saying if you want, you watch it again. Okay, I'm just saying that, so forget about the supremum outside, supremum over n. You consider only whatever in this bracket. Okay, that is the supremum of f of x, where x is in x minus x is in the Fn complement. Okay, but Fn is a set where the Fn is a set where the radon nicotine derivative vanishes. So in the complement, the radon nicotine derivative is strictly greater than 0. Okay, so other way it's absolutely continuous. I mean, this is continuous. This is absolutely, mu n is absolutely continuous with respect to mu. Okay, so in this, outside this Fn, mu and mu n are mutually absolutely continuous. Okay, so when two measures are mutually absolutely continuous, their L infinity norm is same. I mean, a function is in L infinity of one of them, if only if it's in the L infinity of the other one. I mean, because L infinity is just the matter of, you just talk about measure 0 sets. You don't really talk about what the measure is. L2, LP, you are actually doing something with the measure. Here, you don't do anything with the measure. Okay. Here, it is just, it's the same thing. You are only worried about set of measure 0 when you talk about L infinity. Okay. So I'm saying that this is not, so this equality, I think it's clear. Okay. This equality. I mean, I have given the reason orally. You just convince yourself. Okay, this equality is clear. Okay, that's because of radon nicotine derivative. Is it clear? If it is not clear, go through the argument, which I have clearly said, and
Yes.
convince yourself. Okay.
Okay.
Okay. So we have proved that norm infinity is the supremum of this. So then it's clear. Okay. I mean, this is finite if and only if that's finite. All those things are clear. So we have proved two of them. So let us go back again. So I have half an hour more. So we started with the representation pi, which gave us a sequence of measures mu n. And using those measures mu n, we defined a single measure mu. And that single measure mu of that single measure, something is in the L infinity of that single measure, if and only if I fill L infinity of mu n for all n. And that L infinity now is the supremum over all this L infinity. Okay, that we have proved. Now we have that one original representation pi. Okay, that pi is unitarily equivalent to direct sum of pi mu n using some unitary. Using the same, each of the pi of mu n, we can extend to pi of mu n tilde, okay, uniquely, satisfying those convergence, whatever that property. Okay, I mean, that will satisfy, each of those pi mu n will satisfy that convergent property, which we have earlier discussed. Okay, then using that unitary, we get a single representation pi tilde, which is an extension of this pi. Okay, I mean, which coincides with the representation on C of x. Okay, we got a representation which is an extension of that. So now we have to prove that satisfies this following property. We got a representation. Now we have to prove that satisfies this convergence property. That's what we want. Okay. Okay. So proof of 2. So what do you want to prove? We want to prove that suppose Fn converges to. So first we will consider this is measure theoretic. First statement is measure theoretic. Fn converges in mu with f, then which I can leave it as an exercise, which I will just write the corresponding inequality, then it will be clear. Fn converges to f in mu. Okay. Then one way is of course clear. I mean, if Fn converges to f in each mu n, then each epsilon is greater than 0, so it's clear. Okay. Clear that Fn converges to f in for all n, then this is true. Okay. Now suppose Fn converges to F in. No, sorry, the other way is clear. Sorry. Fn converges to, then this is true. Right? Let us do it. Mu n of Fn minus F. This is the criterion for convergence in measure. Okay, is certainly less than or equal to some epsilon n times mu. So epsilon n times this is less than or equal to mu Fn minus F greater than or equal to epsilon. Okay, if you want, you use some eta or something. Okay? Now this goes to 0. That should go to 0. Okay, so convergence in mu measure implies convergence in mu n for all n. Okay, so that we have. Now, suppose Fn converges to, okay, sorry, there is the same n, so use n. Okay. Now Fn converges to F in mu n for all n. Okay. Then we want to prove that it converges in measure mu. That's what we want to do. So we want to consider, of course, mu of Fn minus F greater than or equal to some epsilon. But then this is equal to summation some n, a capital N. I mean, let's assume that it's an infinite sequence. Finite sequence will follow from the proof itself. Okay, finite thing is not a problem. So n equal to 1 to some n. Okay, times epsilon n mu n of Fn minus F greater than or equal to epsilon. Okay, plus summation n equal to n to infinity. But then that is something. Some you can take the whole set itself. Okay, epsilon n mu n. This is less than or equal to mu n of x. Okay. So now each mu n is a finite. I mean, this point is each mu n you can take it to be a probability measure. Did I say that anywhere? So what was the original thing? I mean, it takes identity to identity. You can see the point is this. Maybe I didn't mention. See, if we have a cyclic representation, we are talking about cyclic representation. This is digression. Okay. So we have what we have is we have cyclic representation. Okay, pi mu n is cyclic. Okay, with some cyclic vector. Norm xi, cyclic vector with cyclic vector, cyclic with cyclic vector. Norm xi equal to 1. Okay, and we know that this pi mu n xi pi mu n of the one element is equal to the integral of this. Xi is a function. Okay, this L2 L2 function. Okay, integral of mod xi. But then this is a unit vector. So pi mu n of 1 is 1. So this should be equal to 1. Xi is the, I mean, xi is the constant function 1, right? In the L2 mu. So mu n has to be G0. This is the cyclic vector is G0. Okay. We don't need all these things. This implies mu n is probability measure. Mu n of x equal to 1. Okay. Right? Okay. So you just convince yourself. I mean, it's a pi mu n is a representation and it has cyclic vector this G0. Okay. If you take this state, this state pi of x xi, g naught, okay, pi mu of g naught, that is just integral over norm g naught square d naught. Integral of x g naught, maybe f, let me put f, which is just integral f g naught square, f mod g naught square, whatever. When f is 1, this is just g naught is also constant function 1, which just implies that this has to be 1. Okay? So mu is a probability measure. When you have the cyclic vector as cyclic vector is a unit vector, then the measure corresponding to the whatever we get is a probability measure. Okay. So that if you go through the original theorem where we consider cyclic vector, every cyclic representation of pi mu is given by a measure. That's what we prove. Then we use John's lemma to get the sequence of direct sum of mu. Okay. And that cyclic vector, if the cyclic vector has norm 1, then that mu is a probability measure. So all this mu n is a probability measure. So this is equal to 1. Okay. So summation sigma n is 1. So you can make this less than very small. Then in this, each of this is just a finite thing, then which you can make it small. So this will go to 0. Okay. That's what we want to do. We are proving the other way. Fn converges to f in mu. Fn converges to f in each mu m. Then we want to do Fn converges to f in mu. Okay. So for that, I just write this inequality, where the first inequality, they are just for each of them that goes to 0. That's just a finite sum. You choose a n such that the second part is less than epsilon. Okay. Then the first part is just a finite sum, and each of them goes to 0. So the sum will go to 0. Okay. So you choose n such that summation epsilon n equal to n to infinity is less than some eta. Okay. Because epsilon is there, I'm using eta. Then you make the finite thing, that's just a finite sum, that will go to 0. Okay. Is this fine?
Yeah.
Sorry, I can't show everything here, but I think the whole proof is here. Using a single measure, using a sequence of measure mu n, we got a single measure, and convergence in measure in each of those mu m is equivalent to saying convergence in measure mu. And we just use this. That measure is defined through some epsilon m. And by using that, we get this inequality. We get this. I think it's clear. Okay. So convergence in measure of each of those mu m is same as convergence in measure of this. Okay. 15 minutes. Now let's come to the second part. What did I write here? Yeah, this equivalence condition. Maybe I call this 1. Maybe it's A. This is B. This is C. Okay, we have proved A is equivalent to B. We want to prove B is equivalent to C. So A is equivalent to B. Okay. Now B, we want to prove. To prove B implies C, and then C is equivalent to B. What is B? B means you take some sequence Fn contained in L infinity of mu m. Okay. So Fn converges to F in mu m. Then we want to consider pi tilde of Fn. Okay. We want pi tilde of Fn converges to pi tilde of F strongly. The strong topology. But Fn converges to mu, Fn converges to F in mu m implies pi tilde of mu m Fn converges to pi tilde of F mu m strongly. Sorry. Right? That is the lemma we proved some time back. Okay. So you have a direct sum where each each of them converges strongly. Then the bigger thing also converges strongly. That one needs a proof of it. That will follow from the following. So this follows. Okay, maybe I will prove the other way and then come to this. This follows from the following lemma. Follows from lemma. You have a sequence of operators. Tn converges to T. HB is Hilbert space. Okay. And S is contained in H is total. You know what is total? You take the span of this S. You take the R is dense is also okay. We are using only dense, but it's this more general. Span of closure of H is equal to H. Okay. So suppose Tn contained in Tn is a sequence in B of H. Okay. And Tn, then Tn converges to T strongly is equivalent to saying Tnx converges to Tx for all x in S, and supremum of this norm Tn is less than, norm Tn is less than. It's uniformly bounded and Tnx converges to Tx. Okay, so we will come back to this lemma. From this lemma, it is clear. We have this pi tilde is a direct sum of pi mu n of Fn, pi mu n. Okay, we have that pi mu n Fn converges. So our Hilbert space is a direct sum Hilbert space for where each coordinate wise this converges. Okay, but then the span of those coordinate thing is the original big Hilbert space. Okay, I mean this pi tilde. Okay, pi tilde of this pi tilde. See, up to a unitary, this pi tilde is acting on some direct sum. Where is this here? This pi tilde is up to a unitary, it's like a direct sum of pi mu n. Okay. So this is acts on some direct sum of L2 mu n. Okay. So this pi tilde of L2 mu m coordinate wise, I mean in this direct sum, in the coordinate means Hilbert space coordinate. I mean it's a direct sum of Hilbert space. If you restrict it to one particular direct sum, this pi mu n tilde converges strongly. Okay. Right. So then I want to say that, so the pi tilde restricted to this coordinate is just this pi mu m tilde. Okay, so pi tilde, when you restrict to this coordinate, it converges. So if you take this S is this set, all those xm, such that xm equal to 0 for all m not equal to m naught. Okay, which is just the single coordinate. Okay, for some particular m naught, for some m naught. Okay, then this pi tilde restricted to this S converges, and pi tilde mu m is and this we have that it's originally we have this, it's uniformly bounded. That's because of and this representation is isometric, no? This representation is isometric on each coordinate. So if you take the direct sum, it's just the supremum of that. So it's isometric. Okay, so this pi tilde is also isometric. So it's uniformly bounded. Since Fn is uniformly bounded, this pi tilde is also Fn is also uniformly bounded. So this is uniformly bounded, its convergence on this total set. So this pi tilde of Fn converges. Operator norm is equal to norm f infinity. This is because this pi tilde mu n of fm is isometric that we proved earlier. Okay, the L infinity is isometric. Okay. So then when you have the direct sum where the norm is same in everything, then the norm of the operator is supremum of that. So it's isometric, which is less than the supremum is, which is same as the supremum is less than. Okay. So by that lemma, whatever that lemma we have, this actually converges strongly. Okay. So I would like to know whether it is okay with everyone. If not, you can ask me later also. Okay, you go through this whole thing and you can ask me later. I mean, this is just you have to understand, imagine the whole thing, and that's all. That is really nothing complicated. Once you understand the construction, it is clear. Okay. Okay. So we have proved one way. What we have proved is we have B implies C. Fn converges to F in mu m for all m, then pi of Fn converges to pi of F strongly. The other way is, I mean, we have to prove the lemma. I will come to that lemma. So the other way is clear. Pi of Fn converges to pi of F strongly, then it will converge in each direct sum. So then that is what each direct sum strongly. Okay. So that will imply that. The other way is clear. See. So if pi tilde of F1 converges to pi tilde of F1, F strongly, then pi tilde mu n of Fn converges to pi tilde of mu n F strongly. Okay, because it's just coordinate convergence. Okay, I mean that is a unitary there, but that doesn't matter. Okay, if you write all these things, it will be complicated. Okay, that converges to this. So this implies Fn converges to F mu, and then Fn converges and yeah, that's what we have assumed. That's uniform boundedness for okay. Then sorry, mu n for here also it's m. Okay. So we only have to prove that lemma. So let me pause and ask you whether we have it's with every. I mean, please tell me whether it is okay, because I don't see any of your face, so I don't know whether it is convincing to everyone. I want to ask. If anyone wants any explanation, I can go through the whole thing again. I mean, that's not the point. See, this is just we are studying the representation. We proved something on the representation of C of x. From that, we are extending to a representation of L infinity. C of x is contained in L infinity, and that satisfies some properties like this. Okay. So I don't hear any.
Yeah.
We will go through this.
Go through what?
I mean, we will go through this. I think we will understand.
Okay. So you go through this. If you have a problem, you ask me again. Okay, in the next class.
Yes, sir.
So that's better. Okay. So I have to prove that lemma. I can leave it as an exercise, or okay, there is some time. So this lemma H. I'm writing this lemma again. Hilbert space. S is contained in H total. Okay. Suppose one way is just clear. I mean, then suppose Tn a sequence. I'm not taking nets. I'm taking sequence. Okay, it's important. It will not work for nets and everything. So I'm taking sequence. It will work for. I mean, if you have uniform boundedness, it will work. But the other way will not work. Tn will. I mean, it will one way will work for nets also. Okay? Tn is contained in B of x. But anyway, sequence is enough for us, such that then Tn converges to T strongly is equivalent to saying supremum of norm Tn less than infinity and Tnx converges to Tx for all x in S. Okay. So this way means Tnx converges to Tx for all x in H. Okay. In particular, this is a sequence. So Tnx is bounded. So by uniform boundedness principle, each Tnx is bounded. This implies supremum Tn is also bounded. And then, of course, it converges in the whole space. It will converge in the smaller subset. Okay? So we will have to prove only this way. That way is just you have to write a triangle inequality. You will get it. So span of yes. So we have Tnx converges to Tx on the set yes. So we have Tnx converges to Tx on span of yes. Okay, not the closure. I'm not taking the closure. That is just clear because this is just a finite linear combination, so it will work. Okay, this is true. So now if you have x in H for x prime in H, choose x in span yes, very close, such that x minus x prime is less than some epsilon by something or whatever by less than epsilon is enough. Epsilon by something one may have to do, but let me not worry about it. It will finally turn out to be depends on epsilon. Okay, then we want to consider Tnx prime minus Tx prime. Okay, that is less than or equal to Tn minus Tx prime. That's what I'm which is less than or equal to Tn minus T x minus x prime plus Tn minus T x. X prime minus x. Okay, it's okay, doesn't matter. So now you know that the other part goes to 0, and this thing is uniformly bounded. So this is less than or equal to Tn minus T times norm x minus x prime minus x, then less than or equal plus Tnx minus Tx. Okay, so this thing goes to 0. You can choose. This you must have done several times. You apply choose this epsilon less than this or epsilon by something. Okay. So this is less than epsilon, so you may have to take epsilon by m and epsilon by 2, whatever. Okay, so it's clear. So we have proved the theorem. So I have only 1 minute, so I will stop here. Maybe if I take 15 more minutes, maybe it may not be. I thought that I will prove the spectral theorem today, and then I will not take the class next week. Let me stop recording and we will discuss this.